So let's solve this applied operation to make all array elements equal to 0 problems. This is the fourth question of this week contest. However, this is relatively easy. So let's get started with the problem description first. So basically, you are given an array and also an integer k, and then what you want to do is that you can select any window of size k and decrease all the elements inside that window by 1. So for example, as you can see in the first example here, example 1, so you are given nums like this, 2, 2, 3, 1, 1, 0, and k is 3. So this is returning true. The reason why it returns true is that you can choose the subarray 2, 2, 3 first, and then it kind of decreases it by 1. Like this, basically the first window of size k starting at the index 0, you decrease all of them by 1 and you get something like 1, 1, 2 and then 1, 1, 0. And then next you can apply another operation to make this thing become basically just decreasing this 2, 1, 1 and then it become 1, 0, 0. And lastly, you just decrease this 1 by 1 and it become 0, 0, 0, 0, 0, 0, 0, 0. Basically all 0. So that's why we should return true for this example. So let's look at example 2. So again, we are given numbers and we're also given k equals 2. So this is returning false. Why? Because, well, you can choose this to increase it. So it will basically become 0 and this will become 2. That's the only thing that we can do, because we have to decrease the first element anyway. So the only way to decrease the first element will be choosing the window starting with the index 0. And then we're looking at this to become 2. So we have to do something about this 2 anyway. So we're going to make this as 0. That's why we are decreasing 2 again. And this one will actually become -1. Because if we -2 here, we will also -2 for this one. So 1 minus 2 is -1. And once we see this -1, we will have to return false, because -1 is not allowed, because we can only decrease things. So once it is becoming less than 0, we cannot do anything more to increase it back. That's why we should return false. So that's basically all about it for the problem description. So let's think about how to solve it. So maybe you probably already understand a little bit of the intuition how I want to go with it by how I describe the problem. So basically, even though the first example looks a little bit confusing, they just kind of choose the window randomly. But what you want to do is just basically go all the windows from left to right. So basically, when we meet something here, for example, we meet a 1, then we have no choice but to decrease this one by the value of 1 to make it 0. And this 3 as well. So there is also some consequence of decreasing this 1 to 0, because now you are affecting the remaining things as well. So this will become 2 now. And then this will remain unchanged, of course. And now, if we look at second element, then we have to do something about second element too. And the way that we have to fix it is just decrease this 3 by 2. So basically what we're doing is choose this window and decrease it twice. So that's how we're gonna make this as 0, 0, and this become -1. And this remain unchanged. But we don't have to check anymore, because as I explained earlier, when it reaches -1, it's not going to be an answer. So this is always leading to a solution. So probably we can do this approach for the first example. So what we're going to do is look at the first element. So there is a 2. So there is something that we have to do about it. So what we're going to do is, of course, is just decrease the value of 2 twice. Basically, what I'm trying to do is, because k is 3, so the window size is like this. So I'm going to decrease this window by 2 times to make the first element as 0. Because this is the only way that we can do it. But by doing that, we have some side effect. It will be 0, 0, it will be 1. So then we look at 2, which is 0, which is good. That's what we want. And so we don't do anything. Then we look at 3, there's still 1. It means that we have to do something about it. So what we're going to do is to decrease this by 1, because the remaining value of 3 is becoming 1 right now. So if we decrease this whole window, all this window size of 3 all decrease by 1, and it will become something like 0, 0, 0. I'm sorry if my drawing is not too well. It is very hard to draw using a trackpad. So anyway, you can see that now everything is 0, so that's why we can return true for this answer. So the only tricky part now is how to keep track of those changes, and the outdated part. There's actually a pretty standard way to do it. So if we add if we decrease something here, then we have to notify this index. For example, if we decrease something here, and then we have to notify this index that we have decreased something in here. So the way to do it is just, if we decrease something in index I in general, then index I plus k will be the one that this change is outdated, because the change is only have the size of 3. So that's why on the I plus k we want to refer the changes. So basically we can just maintain an array to keep track of what has been changed. So that's pretty much all for the intuition of, or the idea of, the solution. So the way you do it, based on how I describe it, the time complexity will be O(n), where n is the size of the nums. And actually, for the space complexity will be the same, because we have to keep track of the changes as the deltas. I will call this the deltas way. So we will see more later on for the code implementation. So yeah, that's pretty much all for the ideas. Let's jump into code implementation. Again, I will be using Python to solve the problem, but it should be similar for all languages. So first, we're going to define the size of the numbers, so which is n. And then I will create an array called deltas. These deltas, as I mentioned earlier, is basically used to check when the changes are going to be outdated. So I'm going to also check the decreased value so far, which is basically the delta of the current value. So then now we can just start visiting the numbers from left to right. So first, we're gonna remove the outdated numbers from the deltas. So as I mentioned before, if we do something on, or we do something decreasing something on index I, then index I plus k will be reverted back. So this line 7, basically is how we're going to revert it. So actual value is actually the value becomes numbers I minus the decreased value, because we want to consider the current value, but we also want to consider the changes that we have made before that, because it is possible that we made some changes to the previous window that is affecting the current value of numbers I. So for this if condition, so if actual become less than 0, it means that it is less than 0. So as I mentioned earlier, there is actually no way to increase it back to positive or increase it back to 0. So when this is less than 0, for example, -1, then we are kind of done, that we cannot make this value back to 0 again. So that's why we have to just return false here. So another condition is that if there is some value that we actually want to decrease it, however, if I plus k minus 1 is greater or equal than n, so basically it checks that there is something that we want to decrease. However, there is not enough space for us to do this k size window. So that's why we cannot help but just leave this value as it is, because we cannot do any k size window decreasing from this position anymore. So based on these two cases, we just return false. So otherwise, there's actual value remaining. But remember, we want this actual value to become 0. That's why we have to decrease it. So the way to do it is to just decrease it plus equals to actual. Now we have already considered this actual value decreased. And then we're going to mark this change. Basically, just mark it when this actual update is going to be expired. So as I mentioned it a couple of times, so the time that it expired is I plus k, because right, the window size is k, and I will be the first affected by this k size window, and I plus k minus 1 will be the last one on that window. So I plus k is the first time that this actual change is going to be expired. And then after we do all this for loop, and then we never met anything that is not okay, then it just means that we can kind of sure that we can just change everything to 0. So again, the time complexity is O(n), where n is the size of the array because of this for loop and line 7. And then for the space complexity is also O(n), because obviously the delta's array that we initialize on line 5. So that's basically how we're going to solve this problem. And let's try to run this. Okay, so that's pretty much all. I hope that's helpful, and goodbye.